So good afternoon everyone for the sixth week of interactive session. So in this week we are going to cover what we have left in the previous class. So in the previous class we have started talking about subsurface water, where we have talked about infiltration. And so towards the end of this fifth week we were about to the end of infiltration process. The only thing that was remaining was the concept which is called as ponding time. So in today's class what we are going to do is we are going to cover ponding time. We'll derive what the derivation for ponding time, and we'll take one numerical on ponding time, and that will be the conclusion for subsurface water. And followed by for subsurface water we are going to talk about more in this week lectures is about surface water. So we'll talk about runoff, we'll talk about rainfall hydrograph, then we'll talk about what are the different ways that we can calculate direct runoff, and also at the end of the session we'll talk about two concepts which is called as overland flow, channel flow, and we'll conclude with the stream networks and characteristics of stream networks. So this is what we are going to cover in today's session. So let's start with the concept of ponding time. So first we'll get to know like what is the definition of ponding time. So ponding time, like let us say there is no rainfall at one particular location. So ponding time is the time where the rainfall starts and the water gets infiltrated, and the infiltration is done, and there is ponding of water above the soil surface. So the entire this process, whatever time is required or whatever time is there, that is called as ponding time. So in order to make it more precise or make it more crisp, what we can say that ponding time is the time elapsed between the rainfall when the rainfall starts and the time when water begins to pond. So the time between when the rainfall starts and there is ponding of water on the surface, the time between this event, these two processes is called ponding time. So we'll make it very small. It is nothing but the time between the starting of rainfall or occurring of rainfall and the time water begins to pond on the soil or on the surface. The time between these two things is called ponding time, and the notation for ponding time we'll be using is T of P, TP. So this is the notation what we are going to use for ponding time. So let us see what happens before ponding time and what happens after ponding time. So first we'll take the case of before ponding time. So before ponding time, that is TP. So what happens before TP? Infiltration rate, and we know rainfall intensity. So before TP, the infiltration rate is equals to rainfall intensity. Both are same. That's the reason like whatever rainfall is occurring on the ground, the soil is having more void space in them, because of which all the water is getting infiltrated in the soil. So there is no ponding. That is the first case which we are talking about before ponding time. But what happens after ponding time? After ponding time, what happens is F becomes FP. So in the previous class we have talked about actual infiltration and potential infiltration, right? So what happens after TP is whatever infiltration capacity the soil is having, that is becoming its potential infiltration capacity, which means it is the maximum potential infiltration. So that's the case because of which ponding is occurring onto the soil. So there are many basically the ponding times has been given by two scientists. They are known that the names are Main and Larson. So these two are the person who have proposed the ponding time concept, and how they have proposed, basically they have used three principles. Based on these three principles, they have derived the equation for ponding time. So what they have done is they have used Green-Depth equation model, Green-Depth model, which we have derived in the previous class. So these two have used Green-Depth equation in order to derive equation for ponding time. So what three principles they have suggested? So the first principle that they have suggested is that for T less than Tp, means for the period where rainfall is occurring is less than the ponding time. During that process, all rainfall is infiltrated. The first principle that they have derived. Like if the rainfall is occurring for less than ponding time, then all of the rainfall is infiltrating into the soil. Second principle that they are saying is that potential infiltration means F of P is equals to cumulative infiltration. And third principle they are saying is ponding will occur only when infiltration capacity is less than rainfall intensity. So this we have known in previous class itself, right? That there will be ponding scenario when the rainfall is occurring more and the infiltration capacity of soil is less. So only in that scenario ponding will occur. Right? So these are the three principles that have been given by Main and Larson, and they have used Grindam equation to derive ponding period. Right? So let us see how they have derived this equation for time ponding period. So let us the equation of Grindam model. So the equation for Grindam model, in order to derive cumulative infiltration F was F is equals to K, which is nothing but hydraulic conductivity, is a product of psi, that is suction head, multiplied by moisture deficit divided by F plus 1. This is the equation which we know for Grindam model, right? So let us name this equation as 1. So in this equation what we are going to do, now let us say the rainfall is occurring for a time which is equals to ponding time, when T is equals to T. So what happened during this case? So at this case we can say that the infiltration capacity will become to infiltration rate is equals to rainfall intensity, right? And also cumulative infiltration will become product of rainfall intensity multiplied by ponding time. So now what we are going to do, we are just going to substitute this value of F in equation 1. So this will become I equals to K psi delta theta plus 1 upon I of Tp, right? Now what we can do, we can multiply K inside, right? And then we can solve, and then finally we'll get this equation of Tp, which is equals to K psi delta theta upon I minus K. So this is the final equation. Calculate ponding time. So if we look at this equation, from this equation we can say that the ponding time is dependent on 4 variables, right? And what are those 4 variables? Those 4 variables are hydraulic conductivity K. So we can relate, whenever hydraulic conductivity is more, we can say that the ponding time will be more, which is obvious. Next is psi, which is suction head. So whenever there is more suction head, we can say that the ponding time will be more. The next is moisture deficit, which is delta theta. And last is I, rainfall intensity. These are the 4 things on which ponding times depends, and this is the equation to calculate ponding time. So this is the case when ponding time is there. Now let us see one scenario where what happens to cumulative infiltration after ponding time. So there should be an equation for after ponding time also, like what happens to the cumulative infiltration after ponding time. So let us see a small derivation for that also, and then we'll jump on to the numerical. we are looking at the scenario when what happens after ponding time. Which is T is greater than TP, right? So we already have derived this equation in the previous class. This equation is nothing but equation 1. Now what we are going to do is we are just going to replace T with TP and F with FV. So we are going to take that case when what is happening during the ponding time. So F would become maximum infiltration, that is potential infiltration. And if we subtract this two equation, we'll get a new equation, and that equation is nothing but to calculate cumulative infiltration after ponding time. So if we subtract equation 1 and 2, equation what we are going to use in order to calculate either of the two term, or to calculate cumulative infiltration after ponding time, TP. Now let us take one or two example to understand like how to calculate ponding time. So we'll take one or two examples. Look at this example here. So in this example they are saying for a soil of 30% initial effective saturation, calculate the ponding time and the depth of water infiltrated at ponding subjected to rainfall intensity of 2.5 centimeter per hour, and they have given the constant values on which ponding time is dependent. So let's first write what they have given. So here they are saying that the initial effective saturation is 30%, that is SE is equals to 0.30. Then they are saying rainfall intensity is 2.5 centimeter per hour, and they have given effective moisture content as 0.486, psi equals to 16.68 centimeter, which is suction head, and K equals to 0.65 centimeter. And what they are asking us to calculate two things. First, they are asking us to calculate ponding time, that is TP, and next they are asking us to calculate the depth of water infiltrated. So depth of water infiltrated means they are asking us to calculate cumulative infiltration. That is F of P. Let us see how to do that. So the first thing that we need to do is we need to remember the equation for time of ponding. So we know the equation for time of ponding is Tp is equals to K psi delta theta upon I of I minus K, right? So this is the equation which we have just derived to calculate ponding time. So if you look at this equation from the given data set, we have K, psi and I, but we don't have moisture deficit. But in order to calculate moisture deficit, we need two terms, and those two terms are effective saturation and effective porosity. So that we have. So what we can do, we can first calculate moisture deficit, that is 1 minus saturation, effective saturation into effective porosity. So we'll calculate delta theta. So we have calculated delta theta, and the value for delta theta is 0.3. So now that we have calculated delta theta, what we are going to do is just we are going to substitute the values in the equation of time of ponding. So here they are substituted and they have calculated the ponding time as 0.80 hours. Okay. The next thing that was asked to calculate was depth of water infiltrated, that is cumulative infiltration, and cumulative infiltration is nothing but product of ponding time and rainfall intensity. So we have calculated ponding time as 0.80 hour, and we know the intensity of rainfall is 2.5 centimeter per hour. So the product of that would be nothing but our cumulative infiltration, which is 2 centimeter. Like one of the simplest sum, just to understand like how to calculate ponding time and cumulative infiltration. Now we can take one more sum where they have asked us to calculate what would happen after ponding time, right? So we have just seen the derivation for that also. So we'll take this example. So in this example, they are saying that the rainfall intensity is 4.5 centimeter per hour. So they have given us the value of I as 4.5 centimeter per hour for 1 hour over a soil with initial effective saturation of 30%. Initial effective saturation means S of E value is 0.30%. 30% is 0.30. Then they have given us effective porosity, that is theta E as 0.423. Then given us psi as 29.22 centimeter, and also they have given product hydraulic conductivity K 0.05 centimeter per hour. They are asking us to calculate ponding time, so now we can calculate ponding time, and also they have asked us to calculate the depth of water infiltrated at ponding and infiltration rate. So the first two things that they are asking here is the same which we have done in the recent example, so that we can calculate easily. That is Tp is equals to K psi delta theta on I into I minus K. So first we will be calculating delta theta. So here they have calculated delta theta, the value of which is coming as 0.296, and that value they have substituted here in the equation of Tp, and they have calculated Tp. Then what they are asking us to calculate cumulative infiltration. So that is nothing but I of Tp. So they have calculated F of P also. So the first two terms that they have asked is simple. We have seen it before also. Now let us concentrate or focus on the third thing that they are asking. Now they are asking is cumulative infiltration and the infiltration rate. So we know the difference between these two terms. Cumulative infiltration is nothing but the depth of water that is infiltrating, and infiltration rate is nothing but the rate at which the water is infiltrating, right? And we also know like what is the relation between each of them. So if we have infiltration rate, we'll take the integration of it and we'll get cumulative infiltration, and vice versa is the case for infiltration rate. If we have cumulative infiltration, we'll take derivative of it and it will give infiltration. And we also know the equation for both of them. So what we are going to do, they are asking us to calculate both of this for a case after the ponding time, right? So we know the equation for cumulative infiltration, how to calculate cumulative infiltration after ponding has happened. So we'll take that equation, and that equation is, this equation is nothing but that equation which we are supposed to use to calculate infiltration after ponding has occurred. So let us see what values do we have. Just now we have calculated the potential infiltration F of P, which is nothing but the product of I of Tp, which is 0.10, and also we know that the ponding time is 0.02 R. So we have calculated this value. We are just going to substitute all the values in this equation, and this equation will be in the terms of F, which is unknown, which is the cumulative infiltration which will happen after the ponding. So this equation will be there in terms of F. Now what we are going to do, we are going to do a repeated substitution in order to get LHS equals to RHS. So we have to take our own intuition and go ahead with any value of F until and unless LHS becomes RHS, right? So what we are going to do, we are going to use the method of successive substitution until and unless both the terms on either side of the equation becomes same. So here first we have started the iteration with the value of F as 0.05. So when we are taking the value of 0.05, the answer we are getting is 0.1. So you can see the first case, when we are substituting F equals to 0.05 on the right hand side, we are getting F equals to 0.1. Now what we are going to do, whatever result we are getting in the first iteration, that will be your input for second iteration. So now we are going to substitute F as 0.10 here, and we'll get the value of F equals to 0.15. We are getting here 0.15. Now for third iteration, this will be your input. So we are going to repeat this step until and unless you get both the equation on either side as same. So here you can say that after 58th or 59th iteration, they are getting F equals to 0.96. So we can say that the value of cumulative infiltration is 0.96 centimeter, right? Now that we have computed cumulative infiltration, we know the relation between infiltration rate and cumulative infiltration. So this is the equation to calculate infiltration rate if we know cumulative infiltration. So we know all the terms. We know hydraulic conductivity, we know suction head, we know moisture deficit, and also we know cumulative infiltration after ponding time scenario. Right? So using these terms, we can calculate infiltration rate small f here. So that is what we have calculated. The infiltration rate is 0.50 centimeter per hour. So these two are the examples which can be used in order to solve the equations on numericals on ponding time. Now there is one more example here which is based on Green-Amt equation, right? So in the previous class also we have used. So here they are asking us to calculate ponding time. They are saying ponding depth can be neglected. And they are asking us to compute infiltration rate and infiltration, cumulative infiltration. 1 hour of infiltration into soil that initially had an effective saturation of 0.50, right? So we are supposed to calculate infiltration rate and cumulative infiltration, capital F. So what we are going to do, we know the Green-Amt equation, right? We know f of t is equals to k of t plus psi delta theta ln plus f of t of psi delta theta. So first we are going to calculate those terms that are required in this equation. So we know the value of k given. So we are going to form an equation which will be in terms of f of t, right? So we have created this equation which is in terms of f of t. Now what we are going to do, we are going to substitute the value of ff to t, and again we are going to use successive summation until and unless LHS becomes RHS. So for first iteration we are using time as 1 hour, right? And we are taking a trial value of f of t as 0.34 centimeter, right? Because when t is 1 and value of k is 0.34, so the product of kt becomes 0.34. So here we are substituting value f of t on right hand side as 0.34, and the result we are getting is 0.66. So again, if we are going to repeat the same step, so we can say that after 19th or 20th, 18th iteration, we can see the value of LHS and RHS are same. So we can say that the value of f of t is 0.66. So we can conclude that cumulative infiltration is nothing but 1.64 centimeter. So once you get the value of cumulative infiltration, it is quite easy to calculate infiltration rate, right? So using the same equation which we had used in the previous sum, we know in cumulative infiltration now we can calculate infiltration rate. So this is the case where they have neglected ponding time, and other two are the example where they have considered ponding time. In one case we have considered after what happens after ponding time also. So here we can conclude with the first part of previous week, which was subsurface water, right? So we have concluded here with the subsurface water. Now what we are going to do is we are going to enter into a new chapter which is called as surface water. In surface water, what we are going to do, initially in previous class also we have discussed about the definition of catchment, like what is catchment, what is watershed, right? So the only thing that is left is we should know what is surface water. So in previous week we have covered surface water definition also and surface water definition also. So just to have a small brief about surface water is nothing but the water which is stored on the earth's surface, right? And we can say that surface water continuously interacts with atmospheric and subsurface water, right? So these are the 5 topics now which we are going to cover in the remaining part of the lecture, or in remaining part of today's session. So the first thing that we are going to talk about is a concept known as catchment storage concept, like whatever water is entering into a catchment, so how it is going to be stored. So there are 2 approaches in which the water is stored into a catchment, so that we are going to talk about. The another thing is we are going to relate the relationship, or we are going to see how runoff is generated and what are the factors affecting runoff. Then we'll derive relationship between rainfall and runoff relationship, and later we'll talk about stream flow and measurement of stream flow. So I think in today's week we are not going to start with measurement of flow. This will be covered in next week class. So this would here I think we'll be concluding with our today's session. So let us start with what is catchment storage concept. So if you can see on the slide here, we can say that whatever water is being stored, the majority of is because of precipitation. So majority of contribution is because of precipitation. And once the water enters into a catchment, it is stored in 2 types, that is One is called as retention storage and another is called as detention storage. So the keyword that you should remember is that retention storage is held for a longer period of time. It means the water is stored into the catchment for a longer period of time. So that is obviously it is occurring where? It is occurring in soil moisture storage. And if you talk about detention storage, so this kind of storage is that kind of storage which is stored for a very short period of time. So it will be depleted either by evaporation or outflow from the storage location. So example for this kind of storage is nothing but flood control ponds when water is stored temporarily. So this is like a temporary you can storage, and this is kind of like for a longer period, or we can't say permanent, but it is for a longer period of time. So retention is stored for a longer period of time and detention is stored for a shortened period of time. Now there are different storage components, like where the water is being stored in a catchment. So there are different storage components. So that we can divide into like 5 stages. The first stage is which we can call as interception storage. So interception storage means whenever water is occurring, obviously we have forest cover on the ground surface. So what happens is the water is not directly coming onto the ground surface. It has been intercepted by the trees or branches of the leaves or branches of the trees. So that kind of storage is called interception or interception storage. The other is called depression storage. What happens when the water is stored into the catchment? This kind of storage is done when there is depression on land. So we can say that depression storage can be in form of lake, or it can be in form of small ponds. So that kind of storage is called as depression storage. Then next is subsurface storage. Subsurface storage happens when the water infiltrates into the soil, right? And then the unsaturated flow through unsaturated soil near the land surface, interflow. So in the previous lecture we have talked about 2 types of flow, right? One was interflow and one was base flow. So interflow is the flow where the flow is going out to the is entering into a outlet through unsaturated surface zone, right? And once the voids are filled with water, that is the unsaturated zone becomes saturated, then there will be further percolation of water and the water will flow towards the outlet, and that flow is called as base flow. So in the previous class we have talked about interflow and base flow also, right? So the interflow, I think we can say that it is that kind of storage which happens in unsaturated or subsurface area, and in the groundwater storage we know base flow happens. So that kind of storage is called as soil moisture storage and groundwater storage. This is like a representation of schematic representation of disposal during a stormwater event. Now there are 2 important concepts that we should know. First one is called as hortonian overland flow and another one is called as saturation overland flow. So there are 2 concepts. So this concept will help us to know like how the water is entering into a channel, right? So let us see these 2 things. So I'll first give a small brief like what is happening in hortonian overland flow and what is happening in saturation overland flow. So if you look at to the 2 figure here and we can compare, we can just have a schematic comparison, right? So here we can see in the hortonian flow the water is not getting infiltrated, right? So the water is entering into the outlet as a we can say that excessive rainfall, right? Which is called as excessive rainfall. It means the infiltration, they are neglecting infiltration here. So we can say that the water which is entering is runoff is nothing but rainfall minus infiltration. So whatever the rainfall is left onto the surface, that is going to the outlet and it is above the surface. This phenomena is happening above the surface. So the first thing that you should remember about hortonian overland flow is it is happening above the surface. But again, if you compare here in the saturated overland flow, the water is not entering the outlet above the surface. It is entering through unsaturated zone, right? So this is the 2 major difference between hortonian flow, overland flow and saturation overland flow. Hortonians occurs above the surface, saturation overland flow occurs on the unsaturated zone of the soil. Now let us see at what kind of medium does hortonian flow, overland flow require. So it requires impervious surface, right? And also the infiltration capacity should be low. So these 2 are the favorable conditions where we can apply hortonian overland flow. The first is the surface should be impervious, and the second is it should have low infiltration capacity. So then these are the two cases where we can apply overland hortonian flow. The conditions that supports a saturation overland flow are, it can be applied to the bottom of hill slopes, right, and near the stream banks. So these are the two conditions that are favorable for hortonian and saturation overland flow. So if you want to summarize the overall concept of saturation and hortonian overland flow, we can summarize from this slide. The slide says that in hortonian overland flow, the soil is saturated from above by infiltration. Means first the infiltration will occur, and then whatever water is left, that will be overflowing and getting and it will enter outlet through when the soil is saturated, but it should be above the surface. In saturation overland flow, it is saturated from below the subsurface flow. Subsurface flow means unsaturated zone. So the water is entering to the outlet through unsaturated zone, which is called as subsurface flow, or we can also call it as interflow. So this is all about two concepts, which is hortonian overland flow and saturated overland flow. So we have covered first topic, which was about catchment storage concept. So here we have talked about what are the different types of storage. So there are two types: retention and detention. Then there are different storage component, which is interception, depression, soil moisture storage, subsurface storage, and groundwater storage. Then we talked about two important concept of overland flow. One was hortonian and one other was saturation, right? Now let us see what is excess rainfall and what is direct runoff. So here from the here it is written like it is that rainfall or excess rainfall is that rainfall which is neither retained on the land surface nor infiltrated on the soil. So what happens to the excess rainfall? It is saying after flowing as overland flow, excess rainfall becomes direct runoff and at the watershed outlet. So in order to understand excess rainfall, there is a graph. We can analyze this through graphically also, and that graph is nothing but it is called as hyetograph, excess rainfall hyetograph. So this excess rainfall hyetograph is nothing but it is a graph between excess rainfall versus time, and this will help us to identify the relationship between rainfall and runoff. So if we want to understand the relationship between rainfall and runoff, we can use excess rainfall hyetograph and we can derive a relationship between rainfall and runoff. So let us first see what is abstraction. So abstractions we have studied in the very first week of our course. Like abstractions are nothing but the losses that are happening. So the abstractions, we can say that there are different types of abstraction. First we are talking only about initial abstraction. So the initial abstraction are those abstraction which comprises of interception losses and depression losses. So now we know what is interception storage, because now we can relate what can be interception loss, because we know what is interception storage. So whatever water is being stored through forest cover or through branch or leaves of trees, we can say that kind of water loss is called as interception loss. So here we have said that interception of precipitation on vegetation above the ground. So on vegetation here is the keyword. So interception losses will occur wherever there is vegetation. Next they are saying as depression loss. So what they are saying, we know what is depression storage now, that water is accumulating over a small surface. That small surface could be a lake or small pond. So in that, whatever water is being lost through evaporation, that we can say that it is depression loss. So these two terms comprises of initial abstraction. Now there are many different ways to calculate excess rainfall hyetograph. So there are 4 different ways. So let us see one of them one by one. So the first is we can calculate excessive rainfall hydrograph using phi index, right? Then there is something called as runoff coefficient. Then there is infiltration equation, and then last there is SCS method. So let us see each one of them. So first we are going to cover phi index. So what does phi index do? Phi index will give us a constant rate of abstraction, right? And whatever, if you look at on the figure on the right hand side, it divides the hyetograph into 2 regions, right? So if you can see the phi values here is constant. So it is a constant rate of abstraction that will yield an ERH with a total depth equal to the direct runoff over the watershed. So if you can look at the equation here RD is nothing but Here RD is the value of your direct runoff. And how you can calculate? You can calculate them by using the equation of summation of m equals to 1 to m Rm of phi minus delta t. Here, so here phi index is determining by selecting a time interval of observing the time interval of m of rainfall that actually contribute to direct runoff, and then we can adjust the value of phi and m so that the depth of direct runoff and excess rainfall are equal. So we need a constant line which will divide our ERH value, and based on that we can calculate our direct runoff value, which is RD. Then there is another approach which is called as runoff coefficient. So using runoff coefficient also we can calculate the value of direct runoff. So the runoff coefficient is nothing but the ratio of peak of RT divided by the average rainfall intensity. The most important method is by using SCS method to calculate abstraction, right? So let us look at into brief of SCS curve method. How SCS curve method is used to calculate direct runoff. So if we talk about SCS curve method, so we are talking about SCS curve method here. SCS curve number method. So this method is used to calculate effective runoff, right? It is used to calculate effective runoff. So here we are naming effective runoff as P of E. So there are two initial hypotheses here to calculate effective runoff based on SCS curve number method. The first hypothesis is that the ratio of actual retention capacity of a catchment is equals to potential. So they are saying that the ratio of actual retention capacity of the catchment to the potential retention capacity of the catchment is equals to actual runoff is equal to the ratio of actual runoff and potential runoff. So this is the first hypothesis that is used in SCS curve method. And so now we can look at into this as numerically also, right? So actual retention is given by f of a, potential retention is given by s, actual runoff is given by p of e, and potential runoff is given by p of I minus a. So the second hypothesis is given for initial abstraction I of a. So now we know that initial abstraction comprises of what? It comprises of two things, that is interception losses and depression loss. So the second hypothesis they are saying that I of a is nothing but it is product of lambda times of potential retention, and this lambda, the value of lambda could be 0.2, it could be 0.3. So this is nothing but the second hypothesis that they have used. We know that the actual runoff is nothing but it is sum of potential runoff plus initial abstraction plus actual retention. So we can name it this equation as 2, we can name this equation as 1. Now we can substitute the value of P in equation 2, and we can derive a next equation which is for actual retention, and this equation will become P minus I of A square upon P minus I of A plus S. So this is the equation which is used in SCS curve number method to derive or to obtain excessive runoff, P of E. If we substitute the value of I of A as 0.2, then we can again further modify this equation, and that equation would become P of I equals to P minus, if I am taking I of A as 0.2 times of S. So here I of A will become minus 0.2 times of S, and this is 1 of S. So this will be P plus 0.8 times of S. So we can say that this is the final equation. So in order to calculate excessive runoff, we need two things. The first thing is we should know what is the actual runoff that is happening, and the next thing we should know is what is the potential retention capacity of the catchment. So this value of S, it depends on a number which is called as curve number, right? So curve number is what? It is a parameter which gives us the representation of what would be the retention capacity of that catchment. So to calculate the value of S, we take use of curve number. To find S, we take use of curve number. It is Cn. So that there is some kind of relationship between retention capacity S and curve number. So let us see what is that relation. So first I'll write it down mathematically, that is S is equals to 25400 divided by curve number minus 254. So if we make use of this equation, we'll get the value of retention capacity in mm. Right, so this is the equation. Now let us see what and how we can see what is curve number, right? So the curve number, it can have any value between 0 and 100. So let us take both the case and see if the value of Cn is 0, what kind of surface will have, and what if the value of Cn is 100, what kind of surface will have. Let us say when the Cn value is 100. So what does this implies? So when Cn is 100, it means that the catchment is completely impervious. The catchment is completely impervious. It means if value of Cn is 100, if we substitute here in this equation, right, we'll get the value of S as 0, means there is no retention. It means the surface is of what we can say that the surface is more of kind of urbanized area. So the value of Cn 100 means the surface is more kind of urbanized, so it means there will be less infiltration, right? So it means S value will be less. And for second case, if the Cn value is 0, it means the catchment is completely pervious. So this could be case where if Cn is 0, it means that there is more perviousness. We can say that implies a water body. So if Cn number is less, S will be more. Then we can say that if Cn value is less, it implies that the surface is vegetated surface. So for what vegetated surface, we know infiltration will be more. So if value of Cn is less, we can say that the surface is vegetated surface. Now there are certain things also that we should consider in order to calculate Cn. So the value of Cn, it relies on, first term is, we call it as antecedent moisture content. So value of Cn depends on antecedent moisture content, and also it depends upon the type of soil which is there. So there are 4 group of soil, that is group A, group B, group C and group D. Each group implies the what we can say the perviousness of the catchment, right? So there are 4 group of soil. So it depends on antecedent moisture content, and also it depends upon group of soil. So there are 4 group of soil: A, B, C and D. So if we talk about whether the group of soil belongs to group A, so for group A we know that the runoff will be less. So here runoff is less, it means infiltration is more, it means the value of Cn will be less here, right? The second case, apply for moderately low runoff, group B. Then there is moderately high, and last one is for high. So here we can say that here the Cn value will keep on increasing. Initially it will be less when runoff is less. When runoff keeps on increasing, Cn value will also keep on increasing. So these are the 4 group of soil. On this group of soil also Cn value depends. Then there is antecedent moisture condition. So antecedent moisture condition is also divided into 3. 1, 2 and 3. So antecedent moisture content will give you the information about the initial moisture content. So if you talk about antecedent moisture condition for first case, it means that soil is dry, so condition is dry. For second case of AMC, it implies that it is average, it is moderate. And the third case implies there is a storm event happening. So antecedent moisture content will give us the condition of moisture content which is there initially. So these two things on which CN depends, and also there is LULC. On LULC also CN depends. So on these three things CN will depend, and we'll get the value of CN between 0 to 100, and that we are going to substitute in order to calculate the value of retention capacity. Once we get the value of retention capacity, that is S, based on the value of S and using this equation we can calculate excessive runoff P of E using the equation P minus 0.2 of S square divided by P plus 0.8 of S. So these are the different ways from which we can calculate excessive runoff. So here you can see that the curve numbers are dimensional number derived on the type of soil type and land use, right? So just I have mentioned, like there are 4 groups of soil, and the land use are of 3 types: cultivated, forest and wasteland. Then we also talked about antecedent moisture condition. So we know there are 3 groups, 1, 2 and 3, and it depends upon the, it gives the idea of like the soils are dry initially for AMC1. Second state that it is average condition, and third condition states that there is a storm event or heavy rainfall, right? So we have discussed this. We have seen the equations also. Now what we are going to do, we are going to take a numerical example for SCS curve number first. So let us see this example. Here what they are saying is there is a catchment which has 2 types of soil, right? So the catchment is having type B soil 40% and type C soil 60%, right? And the land cover is 50% good condition, half wooded and half residential. So there are 2 land use and there are 2 group of soil. So that's the reason they have divided land use first. So land use is divided into 2 types. First is wooded. So for wooded also there are 2 types of soil, B and C. And next is residential, right? And for residential also there will be B and C. Then what they are doing is they have mentioned that the entire land use for wooded area is divided into 2 group soil. Group soil is divided is covering 40% of the land use, and group C soil is covering 60% of the land use, and the land cover is itself 50%. So what we are going to do is we are going to take 50% of 40, which is 0.2 for group B soil, and similarly 60% of 0.5 will give us 0.3. What we are going to do is we are calculating a weighted CN, that is average CN for all the condition. So in order to calculate weighted CN, we should get the value of individual CN first. So that we have taken that for wooded soil, that for a wooded land use land cover having group B soil, the CN number is 55. And also for a wooded land use for a group C soil, the CN number is 70. The value of CNs are standard. It depends upon, we know which type of land use is there, which type of soil is there, and what is the AMC condition, right? Here they have mentioned in the question itself the moisture conditions are normal, that is AMC 2 condition they have mentioned. So using these 3 values or three given data set, we got the value of CN, and also we got the value of percentage. So now we can take weighted CN. Weighted CN is nothing but the product and addition of column 3 and column 4. So we got an average CN value of 71.9 for entire catchment, right? And also in the data set they have given us direct runoff of a storm of 150 mm. That is, they have given us the value of capital P. So since we know the value of CN, now we can calculate the value of potential retention S, right? So we got the value of potential retention 99.27 mm. So we got the value of S. Now that we know the value of S, we know the value of P, we can calculate direct runoff, that is PE. So we got the value of direct runoff PE is 73.67. So this was the example based on SCS curve method to calculate direct runoff. Now there are different other method also. So now what we are going to do, we are going to take an example for based on phi index. So let us see this example. Here they are asking us to estimate the runoff at the outlet of the catchment, like what amount of runoff is going to be there at the outlet of the catchment if we know the value of time period and rainfall intensity, right? So they are saying the following table represents the set of observed rainfall data for 70 minutes at an interval of 10 minutes in a watershed if the value of phi index is 4 centimeter. So the value of phi index they are given us as 4 centimeter per hour. They are asking us to estimate the total runoff at the outlet of the catchment. So here you can see we know the time period, we know the rainfall intensity, we know the value of phi. So what we are going to do, we are going to calculate excess rainfall. And how we are going to do that? We are just going to subtract phi index with the rainfall intensity with phi index. So initially we know that excess rainfall can't be negative, so we have written here as 0. Because 2 minus 4 will be minus 2, but excess rainfall cannot be in negative, so we are writing that it as 0. The next is rainfall intensity is 5, phi index is 4, so excess rainfall would be 1. So our aim is to calculate excess rainfall in centimeter per hour. Once we know the value in centimeter per hour, all we need to do is we just need to multiply it with the time period to get the value of runoff. So if we look at this column here, this column gives us the intensity of excess rainfall, which is in centimeter per hour. We know the time interval is 10 minutes. So if we multiply excess rainfall with time interval, we get the value of runoff. But the condition is that we need to convert minute into hours, right? So how we can do that? We can divide 10 by 60. So we can multiply 1 into 10 divided by 60, it will give us the value of runoff for that time period, right? Then again 4 multiplied by 10 divided by 60 will give us the value of runoff, and at the end we need to calculate what is the total runoff at the outlet of the catchment. So all we need to do is we need to take the summation of last column of runoff. So the total amount of runoff is 1.84 centimeter. So this is the numerical where they have already given us the value of phi, and they are asking us to calculate the runoff value. Now let us say let us see another case where they are asking us to estimate the value of phi by giving the value of runoff and excess rainfall. So let us see that case also. So now we are looking at an example where they are asking us to calculate the value of phi. So let us take an example where they have given us the value of time, and also they have given us the value of incremental rainfall. Time period is, let us say, 0, 1, 2. So this is the time period and this is in hour. The unit for this is hours. And we have incremental rainfall also, which is in centimeter, and the value for that is, for 0 it is 0, and they are asking us to calculate the value of phi. So whenever we are using phi index, what we are going to do, we are just going to plot the rainfall hyetograph first, right? So we are going to plot incremental rainfall versus time, and based on that graph we can calculate phi. So for 0 it is 0, for 1 it was 0.5, for 2 it is 1.15, it is 1.5, 1.90. So this value is 2.1, 1.9, 1.15, 0.5, right? So we have plotted this hydrograph. Now what we are going to do, we need to use the equation which we have seen during the during the theoretical part of phi index, like how we can use phi index. So the equation was direct runoff RT is equals to summation of m equals to 1 to capital M Rm minus phi of delta theta, right? So this is the equation which was given. From this equation we are supposed to now calculate phi index. So what we are going to do, we are going to take trial and error method. So first what we are going to do, we are going to assume that the value of m is equals to 1. So we are going to take only one condition, that is m is equals to 1, and we are going to substitute the value of, if we are taking m as equals to 1, it means that the rainfall is 2.1 here, and we are going to calculate the value of phi. So for this we need, they have given us the value of rainfall excess also in the given data set. Here they have given us the value of rainfall, relative rainfall also, which is 0, 0.50, 1.65, 3.55, 5.65, 6.80 and 7.75. So this is the value of RD. So for this case, when the value of rainfall is 2.5, we know the value of direct runoff, which is 3.5. So 3.5, 2.1 minus 5 into time period is 1, because time interval is 1. So from this we can get the value of phi. So the value of phi which we are getting here is minus 1.4 centimeter per hour. So this is not at all possible, right? For this condition the value of phi should be between these two value, right? 1.9 and 2.1. So here it is coming, it is negative, it means this assumption is wrong. Now we are going to take next assumption, that is when the value of m is equals to 2. We are going to take this condition. So if you are going to take this condition, this implies that the value of phi should be between 1.15 to 1.9. And for this instant also we know the value of RD is 3.5. So 1.5 minus 5, sorry 1.9 minus 5 plus 2.1 minus 5. And if we can calculate this value, it will give us, we'll get the value of phi as 0.05 centimeter. So again the assumption is wrong. Value of phi should be between 1.9 and 2.1, but we are not getting 1.9. So similarly we will keep on trying for each case till the assumption is getting right. So if you look at the last case, that is this case where m is equals to phi. So this implies that the value of phi should be between 0.5 and 0.95, right? And we can use the same equation, 3.5 equals to 1.15 plus 0.90 plus 2.1 plus 1.15 plus 0.9 minus 5 times of phi. And if we calculate this, the phi value is coming as 0.75 centimeter per hour. So if we take this case where m is equals to phi, and the phi index value should come between 0.5 to 0.95, so the assumption is right. So we can say that the value of phi index is 0.75 centimeter per hour. So there can be two possibilities or two types of numerical that could be asked. from this concept. First is that they'll simply give you the value of phi and x and they'll ask you to calculate the runoff value. And the other case is this one where they'll give us the value of rainfall and runoff and they'll ask us to calculate the value of phi index, right? This is about all about the relationship between excess rainfall and direct runoff using 4 different approaches. Now let us come to the very end of the topic, that is we need to understand two concepts here. The first is called as overland flow and the other is called as channel flow, right? So here they are saying that there are two types. Basically the flow types can be divided as two: overland flow and channel flow. The overland flow is a flow which has a thin layer of water flowing a wide surface, and channel flow has much narrower stream with water flowing in a confined path. So for channel flow the path is confined, whereas for overland flow the path is very wide. Now there are two definitions that we need to take into consideration here. The first derivation is for overland flow and the next is for channel flow. So let us do that one by one. So first we'll do for overland flow. We'll take the derivation for overland flow. So if you look at the figure here, so here let us name all the components that are taken here. So the first component that we are going to take is theta. So what is theta here? Theta is nothing but it is the angle between the ground surface and the horizontal, right? The next term is y. So what does y represent here? So the y represent here is the depth, the overall depth, right? The depth of flow which is perpendicular to the ground. The next term is x. So the x here is 1D flow in x direction which is parallel to ground surface. The next term, that is v, velocity. So velocity is nothing but, we know what is velocity. It is velocity of the flowing water, but it should be parallel to the ground surface. And last term is LO. So LO is nothing but the length of ground which we are considering. So there are 5 terms which we have named represented initially. So if we know the value of theta, we can calculate the slope also, right? So they have calculated the value of slope. Now what they are going to do? Now we are going to apply continuity. So we are going to use Reynolds transport theorem and we are going to apply the same thing for the scenario here. So we know the equation of Reynolds transport theorem and we are going to apply continuity equation. So whenever we are going to apply continuity equation, what happens is the left hand side of the term becomes 0, right? So this becomes 0, and also this is the case for steady constant density flow. So the second term, the first term would become 0. So only thing would be left is beta times of rho v dA equals to 0, right? So we have a control surface. Now what we are going to do, we know beta would become rho is constant, so we can neglect it. Beta is also we can neglect it. The only thing left is v of dA. So now what we need to do, we need to calculate v. So we need to calculate v for both the cases, that is inflow which is from rainfall and outflow which is from infiltration. And if we know inflow and outflow, we can calculate the net outflow also. So here we have calculated the inflow, here we have calculated the outflow which is due to infiltration, and this is outflow as overland flow, Vy. And we are going to substitute all these 3 terms in this equation of continuity equation, that is V of dA. So when we substitute this equation, what is left with us is this equation. V of y is equals to I minus f of L cos theta, and we know what is V of y. It is nothing but discharge, right? This is velocity must multiply by depth per unit width, right? So we can say that this is nothing but discharge per unit width. So we get the equation of discharge per unit width as I minus f of L cos theta, where I is nothing but infiltration capacity and f rainfall intensity and f is infiltration rate. So this is the equation which comes when we use continuity equation using Reynolds transform theorem. So there is also something called as momentum equation. So same thing we are going to apply for momentum equation. So this will need some understanding from our previous class of fluid mechanics. That is, we know what is this is the equation that we use for laminar flow down in an inclined plane surface, right? So this equation we are converting it into average velocity. So this is the equation for average velocity V, which is G S0 y square upon 3 times of kinematic viscosity. So instead of kinematic We can write mu by rho also, but here we have taken in terms of kinematic viscosity, right? Now here we know what is SO. So SO is nothing but hydraulic gradient. So here we can write SO equals to H by L. So we have written SO by H by L. And again we have modified this equation, and we have, if you look at this equation, this is nothing but an equation from fluid mechanics which is known as Darcy-Weisbach equation, right? So using this equation we can calculate major loss in a pipe. So this is a similar equation. So now what we are going to do, we are going to compare this equation with Darcy-Weisbach equation. So from this comparison we'll get the value of friction factor F. So if you look at this equation, the value of friction factor F we are getting as 24 nu times of Vy, right? Now what we are going to do, we are just going to modify this equation in order to get Reynolds number. So here you can, so you know the value of friction factor, so you are converting the entire equation in terms of Reynolds number. So if you can see here the Reynolds number value is Vd by nu. So here we can compare Reynolds number is nothing but 96 times by friction factor, right? So this is the case for laminar flow. So same thing we can do and we can apply for turbulent flow as well. So here they have taken the case for turbulent flow and they have derived the similar equation. So this is the finalized equation which they have used for turbulent flow. So I'll be sharing my notes as well. In notes you can get a more generalized equation also. So here we have seen for overland flow for both the cases, that is for laminar and for turbulent, right? So this is all about the theoretical part of this. Now what we are going to do is we are going to take some example that could help us to solve the next assignment, like that is the assignment number 6. So we are going to take few numericals from assignment number 6 as well. So if you look at assignment number 6, they have asked few questions on SCS curve number, right? So we can take one more example so that it could be easy for us to solve SCS curve number, any numerical and SCS curve number. So let us say we have a catchment where they have directly given us the value of Sn, and the value of Sn, their Cn number they have given here is given to us is 75. So we have Cn number as 75, and also they have given us the magnitude of runoff as 110 mm, right? And they are asking us to calculate the runoff magnitude. So we know the value of P, they are asking us to calculate the value of PE. So how we can do that? I think this is very simple sum. If you look at, the first thing that we need is maximum retention S, right, which depends on Cn number. So this will give us the value of maximum retention in mm, and if we know the maximum value retention, we can calculate PE also because we know the equation. Here we need to substitute Ia equals to 0.2 times of S. So if we do that, we get the finalized equation. So once you know the value of S, all we need to do is substitute the value of S here and we can get the value of PE. So this kind of numerical they can ask in the assignment. And also they have asked us to compute effective runoff, right? So they have asked us to calculate direct runoff hydrograph due to an isolated storm, triangular in shape with base of 75 hours and peak of 300 meter cube if the catchment area is 1500 kilometer per square, they are asking us to compute the effective rainfall of the storm. So this sum is quite easy. All you need to do is you just need to calculate the area of the catchment, and then you need to divide the total runoff with respect to the area of catchment. So how you can do that? You need to compute P E. So how we can do that? We need to calculate runoff volume. If we know the runoff volume, we can divide the runoff volume with area of catchment. So I'll give you a small hint. All you need to do is, they have given you the shape of direct runoff, right? They have given us a triangular shape with base of 75 hours and peak of 300 meter cube. So all you need to do is you need to calculate the volume of this. And once you get the volume, you can divide it by the area of catchment, which is given as 1500 kilometer square, and then you can divide and you can compute the value of rainfall. Then they have asked a numerical on to calculate the value of phi index, right? So this numerical, I think we have just solved the same numerical where they ask us to calculate phi index. So you will need trial and error approach. So once your assumption get whatever value of assumption or whatever value you have assumed and it is coming to be true, then you can stop your successive trial and you can conclude the value of phi is whatever your assumption was there. So I think you can do that sum by looking at this numerical. The last sum is also the same thing which we have done in the first class itself. They are asking us to calculate the runoff depth. So all you need to do is you need to subtract your rainfall and phi value, then it will give you the value of excessive runoff depth, and then you need to take the summation of that column. It will give you the excessive runoff. Then there is one more sum that they have asked us to calculate the value of phi index. If you look at question number 11, it is very simple sum. All you need to do is you need to consider the abstraction, and you need to follow the definition of phi index. If you know the definition of phi index, by using that you can calculate and solve question 11 and 12. So assignment 6, I think the last date is due this week. So if you cover all the concept that has been covered in this session and also in the recorded video lectures, I think you will be able to solve the assignment 6 now. So we have covered this numericals and we have also seen SCS curve number. So I think for this week's session, I think there was nothing much. There were only 5 lecture videos, and out of those also there were mostly based on numerical concept. So I think today's session, I think we can conclude early if you don't have any doubt. So for today's session, we started initially first with the previous week session, that is the subsurface water. So in subsurface water, one concept was remaining, which is called as ponding time. So we started initially with ponding time. You know what is ponding time? It is nothing but the time elapsed between the rainfall begins and the water starts ponding. Then we see how Green-Damped equation was used to derive the equation for ponding time. So they have used 3 principles. The first principle states that when ponding time is less than the time period for which rainfall is occurring, all the rainfall would be infiltrated. The second case is the potential infiltration rate, that is Fe, is a function of cumulative function. And the third case is ponding occurs when potential infiltration is less than rainfall intensity. So using this 3 principle, we have derived this equation of ponding time. So if you look at this equation, we can say that ponding time is nothing but it is function of 4 variables or 4 parameters, that is hydraulic conductivity, suction head, moisture deficit and rainfall intensity. So using this equation we can form a relation between TP, ponding time and each of the parameters. So we can say that when we have higher hydraulic conductivity, we can say that ponding time will be more, right? Similarly for suction rate also, for moisture deficit also, and for infiltration rate also, rainfall intensity also. Then we have taken a case where infiltration, what would happen to infiltration after ponding. So we are taking a case where T is greater than TP. So we know this equation of green damped to calculate cumulative infiltration. So we have applied for both the cases, and we have subtracted both the equation, and we got a new equation. So this equation is nothing but an equation which gives you the cumulative infiltration for a after ponding time scenario. Then what we have done is, since we have developed this, derived this two equation, we have seen 3 examples. So we have taken 3 examples. First example was where we have neglected the ponding depth, and we have got the value of cumulative infiltration and infiltration rate. So we have used the green depth equation, we got the standardized equation, and now we have taken successive substitution approach, and we have calculated the value of cumulative infiltration until and unless we got both the terms on the either side to be same. So we got the value of F as 1.64, and since we know the value of cumulative infiltration, we can calculate infiltration rate also using the equation K psi delta theta upon F plus 1. Then we have taken 2 examples on ponding time. So the first example was just to calculate ponding time and cumulative infiltration using the equation of ponding time, which is very simple. We are directly going to substitute the given data set in the equation of TP, and multiplying rainfall intensity with TP will give you the cumulative infiltration. Then we have taken another example where we have also added another case for what will happen to cumulative infiltration and infiltration rate after ponding. So the first 2 cases were same for the prior sum, so we can directly jump on to the third case for after ponding. So for the after ponding scenario, we have this equation. So what we are going to do, we need to calculate F. So we are going to develop or modify the equation where we are going to keep the entire equation in terms of F. So this is the equation. Now again we are going to do successive substitution, and we are going to get a value of F, and with that value of F we can calculate infiltration rate. So by using successive substitution, we get the value of F as 0.96, and with this value of cumulative infiltration we have calculated the value of infiltration rate. So this was all about from last week, which is subsurface water. Now for today's week we started with surface water. So in surface water we are going to cover these 3 topics. The first topic was catchment storage concept, then it was runoff generation and factors affecting runoff, and last it was rainfall runoff relationship. So in today's week we are going to cover these 3 topics. So we started with catchment storage concept, right? So we talked about there are 2 types of storage mechanism. First is retention and detention. So the keyword is retention, it stores the water for longer period of time. Detention stores water for shorter period of time. Then there are different storage components. So we talked about 5 different storage components. We started with interception. So interception, we know the keyword is forest cover or vegetation. Whatever water is stored on forest cover or vegetation, that comes under interception storage. Then we talked about depression storage. That is the water that is stored in different depression on the land, that it could be a small lake or pond. Then we talked about soil moisture storage or subsurface storage, that is interflow of the river. And then we talked about groundwater storage, that is base flow. Then we talked about 2 important flow concepts, right? The first was hortonian overland flow and another was saturation overland flow. So in order to summarize or conclude between the 2, we can say that hortonian overland flow was a flow where the soil is saturated from above by infiltration, and in saturation overland flow it is saturated from below by subsurface flow. So here it is saturated from above by infiltration process, here it is saturated from below by subsurface flow. So the keyword is here above by infiltration and below by subsurface flow. So and also we can look from the figure as well. Here the water is coming as in the form of interflow, that is subsurface flow, and it is entering into the outlet, whereas in case of hortonian flow it is flowing after subtracting the infiltration, whatever water is left it is flowing over the surface and it is entering into the outlet. Then we talked about excess rainfall and direct runoff and the different ways how we can calculate direct runoff. Then initially we talked about initial abstraction. So we know initial abstraction comprises of two losses, that is interception losses and depression losses. Since we have covered all the storage component, we know what is interception losses. So where interception losses would occur and where depression losses would occur, right? Then we talked about different ways to calculate excess rainfall hydrograph using phi index, using runoff coefficient, using infiltration equation, using SCS method. And we have also seen numerical based on phi index and SCS method. We looked into more detailed of SCS method because many of the hydrological model use SCS method. So we talked about the fundamental hypothesis. We have seen the numerical mathematically what are the fundamental hypotheses. Here they have written theoretically as well. They state that the ratio of actual retention of rainfall to the potential retention of potential maximum retention is equal to the ratio of direct runoff to potential. So here we can say the mathematical approach, FA by S is equals to PA upon P minus IA, right? So from continuity principle we know that the total rainfall is equals to excessive rainfall plus IA plus retention capacity. So we can calculate the value of Pi from here and we can substitute in equation 1. So we have done that. Now we know that the initial abstraction. So for initial abstraction we use another null hypothesis. We state that initial abstraction is product of 0.2 times of S or 0.3 times of S. So here we have taken 0.2 times of S by using many small experiments. So we get the overall equation of Pi of PES minus P minus 0.2 times of S square upon P plus 0.8S. So this is the final equation which is used to calculate direct runoff using in SCS method. So now what we need to do is we need to calculate S. Now S is nothing but it is the maximum retention capacity of the catchment, and this value is dependent on SC curve number, right? And the value of curve number depends upon the type of soil and vegetation, type of soil and land use, and also antecedent moisture content. So in order to calculate S, we need to calculate curve number. So now let us see how to calculate curve number. We know that curve number depends upon type of soil and land use. So there are different types of land use. So here we have classified 3 different types of land use, that is cultivated land, forest land, wasteland, and the type of group soils are 4A, B and C, D. So these are the type of soil and their characteristics, and we can also remember them by, we can say that the type soil is deep sand, right? So the runoff would be very less because infiltration would be more, because the void spaces would be more. So similarly we have classified group of soil based on how much amount of runoff is going to take place, whether the runoff is low, moderately low, high or moderately high. Then we talked about antecedent moisture condition, which give us the idea about the initial moisture content. So it is divided into 3 groups, where first group says that the initial moisture content is dry, second says the condition is moderate or average, and third says that there has been a heavy rainfall or storm event within the last 5 days. Then we have seen the equation for Cn for both the conditions, Cn1, Cn2, and then we came on to the numericals. So numericals, we have seen numericals based on SCS curve number method, and also we have seen numerical based on phi index approach, right? So we have seen both the equation, estimation of runoff using phi index and estimation of phi index based on phi index approach. Then we came to the last topic, that was overland flow. Here we have seen the derivation of overland flow and channel flow. And the only thing that was left was stream networks, right? If you look at this diagram, there is an approach given by Horton which help us to name the stream order. So if you look at this curve, when stream order of two streams of order 1 means, it will gives you another stream order of 2. If you look at this 2 and 1, when a stream of stream order 1 and stream of stream order 2 meets, it will give you a stream order of 2. So in order to get a stream of stream order 3, there should be an intersection of stream of two stream orders. So if you can see here, 2 and 2 are meeting, it gives you a stream order of I plus 1. So the generalized format is when two channels of order 1 join, a channel of order 2 results downstream. So in more generalized form, we can say that when two channels of order I join, a channel of I plus 1 results, right? So once we know what is stream networks and what is the stream ordering system, we can look into different characteristics of stream network also. So the first characteristic is nothing but drainage density. So the drainage density is nothing but the ratio of length of stream channels of the catchment to the area. So all you need to remember is length divided by area of catchment. It will give you the value of drainage density. Then there is something called as stream density. So stream density will give you the value of number of streams that are present per square meter. It means how many number of streams are present in your catchment. It will give you the idea about number of streams present in your catchment. It is known as stream density. The next term, then there are different terms also that I think we'll see in next classes for this stream network. So they are defined using only two terms, that is drainage density and stream density. I think in the next week class we'll be continuing from here as well, from stream networks, and then we'll look into how we can measure stream flow, and we can see different approaches of measuring stream flow and numerical based on the measurement of stream flow. So from in next week class, I think we'll cover from stream networks. We'll talk about stream flow, what are the factors affecting stream flow, how to measure stream flow, and numerical based on stream flow. I think this is all about today's week. In next week, we'll cover from stream networks, and we can look into more of stream flow and stream flow measurement. कितने बच्चे हैं? I think we can take few more minutes and we can look at this numericals once again, because I think these are something that will take time. So if you can take few minutes and you can solve this equation and you can see and you can try it yourself, like how successive substitution takes place. So it would be like a practice for you, and you can use those things in your exams also. So the key thing here is whenever you are using successive repetition, whatever output you are getting for your previous iteration, it should be the input for your next iteration. If you are using that approach, I think it would be easy for you to get your desired result soon. Even for this case also we can try and see, because the number of iteration years are coming more. So the number of iteration depends upon what values you are taking on for your initial trial. So here you have started with very quite low value, that is 0.05. We are substituting cumulative infiltration at 0.05 on the right hand side, and we are getting cumulative infiltration at 0.1. So we can always start with some random value, like we can start with 1, and we can see if the values are not coming good, we can reduce that value. So we can start with 0.5, 0.7. So if you can start from 0.5, it means your number of iterations would be less. And also whenever we are getting iterations same for both the on both the side, let us see this here. For iteration 43 or 42, we are getting same values, but we didn't stop here. We have taken more iteration just to make sure whether those values are being constant. So even if you are stopping here at 42 iteration, the result won't change that much. There will be difference of only 0.20 centimeters, so that would be fine. Just make sure you practice once before you get into your before you go for examination, this iteration successive substitution approach once. So just to summarize, like what we have done today in today's session is, first we started with subsurface water. The last concept which was left in last week, that was ponding time. So we started with ponding time, concept of ponding time. We have derived the equation for ponding time. We have taken the case what happens after ponding time to the cumulative infiltration. Then we have taken numericals as well for both the cases. Then we looked into the new topic which is surface water. We started talking about surface water. We started talking about the concept of storage. Then we looked into different aspect of storage. Then we talked about two important concepts of overland flow, that is hortonian and saturation overland flow. Then we talked about excessive rainfall and direct runoff, and what are the different ways how we can calculate direct runoff, that is using phi index or runoff coefficient or SCS curve method. Then we looked into more detail of phi index approach and SCS curve method. Then we have solved numerical as well on both the approaches, and then at the later part we talked about overland flow and channel flow. We derived the equation for overland flow and channel flow, and then at the very end we talked about stream networks, like how how two channels of I order meets and we get a I plus 1 order stream. And we talked about two different characteristics of stream, that is drainage density and stream density. And I think this would be the very end of our today's week session, and in the next week session we'll talk more about the definition of stream flow, factor affecting stream flow, how to measure stream flow, and the different numericals to calculate stream flow, that is based on current meter or based on aerial velocity method, right? So we are going to look that into our very next class. So we'll conclude today's session here, and I hope to see you in the next week session, which will be more about surface water.